Hello students, I'm Tausif and I welcome you all to yet another video lecture. And today's topic is approximation algorithms. The contents of our lecture will be going through the background about the optimization problems. We'll be discussing relaxing the constraints. We'll be giving the definition of approximate algorithms, and then we'll discuss some types of approximation algorithms. An optimization problem asks for finding the best and optimal solution from all feasible solutions. So an optimization problem asks for finding the best, which is also known as optimal solution from all feasible solutions. Now, the goal here can be to minimize the cost or maximize the profit. So there are two goals here. The objective here is to minimize the cost or maximize the profit. We can have two cases of optimization problems where we want to minimize the cost or maximize the profit. For example, as far as minimization of cost is concerned, we can think of a problem which is really famous, also known as TSP. Traveling salesperson problem, TSP. What this problem asks us is that we have a group of cities and a traveling salesperson starts from a particular city and he has to travel all the cities and come back to the city he started from, while considering that it takes him the least amount of cost. Cost may be in terms of money, it may be in terms of distance. So a traveling salesperson has a set of cities he has to travel. He has to travel every city once and return to the city he started from. And our goal here is to minimize the cost of his travel. This is the traveling salesperson problem. Now, one more problem which we can think of as far as maximization of profit is concerned, we have knapsack problem. What is the knapsack problem? It states that we have a bag, a knapsack, which is constrained by capacity. It can only hold some amount of weight or units of products. Our main concern here is to fill the bag with the subset of the available products such that the profit, we have the maximum profit. Like we have n number of products available. And we have bag M or knapsack M, a knapsack with capacity M. We have to fill this bag with a subset of these n products, such that it's constrained by capacity M. It can only hold M units of these products. So such that our profit is maximized. Each product has associated with it different profits. So our goal is to maximize the profit. This is the case of optimization problem where we want to maximize the profit. Every optimization problem consists of three parts. or elements. First, so every optimization problem, it consists of three parts. It has three parts. Right? A non-empty set of instances, rather problem instances, I, an objective function v x y, where y is the feasible solution to problem x, which belongs to I, and a goal to either maximize or minimize the objective function. So we have three parts which every optimization problem consists of. A non-empty set of problem instances I. Our optimization problem can have many instances. And an objective function where of the form vxy, where y is the feasible solution to problem x, which belongs again to the problem instance set I, and a goal where we have to either minimize the cost or maximize the profit. Every problem instance x, which belongs to I, has an ordered pair Sx, opt x, where S of x is the set of all feasible solutions and opt of x is the best or optimal value for the objective function. Now this value, in case of minimization, it will be the least value, and in case of maximization, it will be the maximum value. So every problem instance x, which belongs to I, it has an ordered pair S of x and opt of x. S of x consists of all the feasible solutions, all the solutions that this problem instance can have. But our main concern and our main focus here is to find the optimal value for the problem instance x. We have to find this value, which is our main concern. For every optimization problem, we have to find this value, which is the maximum in case of maximization goal and minimum in case of minimization goal. So this is all about minimization problems. In a nutshell, in optimization problems, we have to find the optimal value. It can be the minimization, it can be the least value for minimization case and maximum value for the maximization case. There is no polynomial time algorithm to solve NP-hard problem. And a large large number of optimization problems are NP-hard. Large number of optimization problems are NP-hard. Now, this may rather seem a discouraging fact that the optimization problems, a large set of optimization problems are NP-hard, and we have no polynomial time algorithms which can solve these problems efficiently. So, what to do? What's the solution now? Before we get into that, since we also are with the thought that P is not equal to NP, it suggests that we cannot find algorithms, which will find exactly the optimal solution to all instances of a problem in time which is polynomial in the size of the input. This is a rather long statement. So, since we are with the thought that P is not equal to NP, which we have seen in previous lectures. Now, that means that since large number of optimization problems are NP-hard, that means it suggests that we cannot find algorithms which will find exactly the optimal solution, because we saw that by solving optimization problems, we are actually trying to find the optimal solution. So, we cannot find exactly the optimal solution to all instances of the problem, to all instances of an optimization problem in the time which is polynomial in the size of the input. So, here there are three important things you have to remember. One is optimal solution. We want to find optimal solution for all instances of a problem. And we want to find optimal solution for all instances of a problem, optimization problem, in polynomial time. If we take all these requirements into consideration, then it's a rather stringent requirement, and it will in the long run, it will hinder us to find any solution in polynomial time. But there are three possibilities. If we relax any one of these requirements, we can come up with a solution. And let's discuss those solutions one by one. So there are three possibilities. These three possibilities are possible only when we are ready to leave any one of these requirements. We are ready to leave, ready to ignore any one of these three requirements. Now, number one. Super polynomial time heuristics. sometimes a problem instance can be solved in a time which is not particularly polynomial but super polynomial, slightly above polynomial. It is solved in a manner which is more fast, more quick than we may assume it may not. For example, there are cases where we can solve a problem in super polynomial time which still runs reasonably fast. In this technique, what we are doing is we are relaxing the requirement for finding the solution in polynomial time, but it still finds the solution in reasonably fast amount of time, reasonably fast. It's not the efficient algorithm, but we can find the solution. If we relax this polynomial time requirement, we can still find the solution reasonably fast. For example, the knapsack problem, which you know now is NP complete. Knapsack problem is an optimization problem, it's an NP complete problem. The first insight would be that this problem cannot be solved in polynomial time. That's right, cannot be solved easily. Actually, it's very hard to solve this problem. But there is a pseudo polynomial time algorithm pseudo-polynomial time algorithm which solves this knapsack problem quite easily. We use the technique of, the techniques of branch and bound and dynamic programming to come up with the solutions by relaxing the polynomial time requirement of our problem. This is our second possibility. Probabilistic analysis of heuristics. Now, if you look at this requirement, it says that the optimal solution should be found for all the instances of a problem in polynomial time. In some of the applications, what this technique, what this scheme says is that if we relax this requirement where we have to find the solution, optimal solution to all the problem instances, then we can find the solution fairly easily. What it says is we constrain the problem instance set. If I have a problem P, it has an instance set I, and this I is constrained by some limit is by some constraint C1, and I'll get a new set of I2. And this set, this I2 here, can be solved fairly easily. I had a problem P, and I have an instance set I for problem P. Now what I do is I apply this constraint here C1 to this problem instance set I, and I get the instance set I2. Now this I2 can be solved fairly easily. For example, Hamiltonian cycle search or finding Hamiltonian cycle. Again, this is NP complete problem, cannot be solved easily. It's very hard to solve this problem. What Hamiltonian cycle says is that if we have a graph something like this, It asks to find a cycle in which each node is visited once and we return to the node where we started. Each node is visited once and we return to the node where we started. One possible Hamiltonian cycle will be like this. So here, 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 here. Right? So this problem, finding Hamiltonian cycle in a graph, it's a NP complete problem. But there's an efficient algorithm which says that I'll find a Hamiltonian cycle in almost every graph if there exists a Hamiltonian cycle in the graph. So the constant here is if there exists a Hamiltonian cycle in the graph, I'll find one. I'll find that. So this is the constant. But what happens if there is no Hamiltonian cycle in our graph? What happens then? So that's a problem. Then it becomes really hard for the algorithm to solve this problem. The constant, so this constant it limits the instance set for the problem finding Hamiltonian cycle. When it limits that, then it solves the problem fairly easily. This is the second technique, probabilistic analysis of heuristics. Let's move forward to the third possibility, which is our main topic today. Approximation algorithms. The third possibility comes by relaxing the requirement of optimal solution. Now, if we relax the requirement of finding the optimal solution, we come across the class of algorithms known as approximation algorithms. What we do here is we try and find, we actually devise the efficient algorithms at the cost of the efficient algorithms for solving NP hard problems at the cost of what? Suboptimal solutions. The solutions we get for all problem instances, they are slightly suboptimal. They are very close to the optimality but not optimal. That's which is actually our third requirement. So we devise efficient algorithms to solve NP hard problems for all problem instances at the cost of generating slightly suboptimal solution. So we find efficient algorithms. That means these algorithms solve the NP hard problem quite efficiently, but at the cost of generating slightly suboptimal solution. The solution we receive is suboptimal, it's not optimal. So these are the three possibilities for solving NP hard problems. Now let's define an approximation algorithm. Given an optimization problem P, if we have an optimization problem P, A is an algorithm. A is said to be the approximation algorithm for P. We have an optimization problem P, and we have an algorithm A. We call this a approximation algorithm for P if for any instance of any instance I of P, comma, the algorithm A returns a feasible solution. This is the definition of approximation algorithm. We have a problem P. The algorithm A will be known as the approximation algorithm for problem P if for any instance of A, take any instance of A, it will return, this A will return a feasible solution for this problem instance I of P. This is known as approximation algorithms. Now there are two types of approximation algorithms. There is absolute approximation, and there is relative approximation. Let's define each one separately. Before we define absolute approximation and relative approximation, I want to use some notations. For example, if P is our optimization problem, and I is our problem instance, a problem instance of P. We have A star of I, the optimal solution to problem instance I of P, and we have A of I, the approximate solution. Returned by the approximation algorithm for problem instance I of P. And we have A, the approximation algorithm. Keeping these notations in mind, let's define absolute approximation. Absolute approximation. A is said to be absolute approximation algorithm Let's write it down here now. A is said to be absolute approximation algorithm if there exists a constant k, if there exists a constant k such that for every problem instance I of P A star I minus A of I is less or equal to K. This is the this is the absolute approximation. The approximation algorithm A, it will be known as the absolute approximation algorithm if there exists a constant K, such that for every problem instance I of P, the optimal solution for I minus the approximate solution for I should be less or equal to this constant K. It can be tolerance or error or whatever. Relative approximation. Again, the approximation algorithm A is said to be relative approximation algorithm if there exists a constant K such that for any problem instance I of P maximum of optimal value of instance I by approximate value of I, approximate value of I by optimal value of I is less or equal to K. So relative approximation says that an algorithm A will be a relative approximation if there exists a constant K for which the ratio of optimal solution and approximate solution, the maximum of the ratios, is less or equal to the tolerance. This is known as approximation, relative approximation. So this is it for today's lecture. I hope you get the idea, the intuitive idea about the approximation algorithms and how we solve NP-hard problems. The important thing to understand here is that NP-hard problems are really difficult to solve. Really difficult to solve. All the algorithms which are used to solve NP-hard problems, they have the worst case time complexity of the order of exponential. They are exponential. They have exponential time complexity. But if we relax any one of the three constraints, three requirements we talked about, then we can come up with fairly good solutions. But again, there's a trade-off. Hope you understood everything we discussed in the lecture. See you in the next lecture. Thank you.
Thank you.